Hi student, we have a new lecture in vector calculus and we're going to learn about Green's theorem. So keep watching this video. What is Green's theorem? It is a transformation between double integrals and line integrals. In the previous videos, we already discussed about line integral and double integrals. This theorem will give us a transformation from double to line or from line to double integrals. So what is Green's theorem? Suppose that C is a piecewise smooth simple closed curve. This is C. C is bounding a simple connected region R. So the boundary of this region R is the curve C, which is a closed curve. If f1, f2, partial derivative of f1 with respect to y and partial derivative of f2 with respect to x are continuous function in R, then Green's theorem states that a line integral along a curve C, closed simple curve C, f1 dx plus f2 dy, giving the same answer as double integration over the region R partial derivative of f2 with respect to x minus partial derivative of f1 with respect to y dx dy. We use this rule to transfer integration from line to double or from double to line, as in the next example. Example, use Green's theorem to convert double integral to line integral. So we're going to transform from double to line, where f1 is given, f2 is given. Both of them are function and they are continuous on our region R. And the region R is bounded by the curve C. C is the circle x squared plus y squared equal to 1. We need to sketch the graph of the region R first. This is our region R. It is bounded by the curve C. C is the circle x squared plus y squared equal 1. To convert the double integrals to a line integral, we use Green theorem, and this is the theorem. Now, to evaluate this line integral, we have to find the parametric representation of the curve C. That means we find R first, then we find f1 at R, and we substitute here, and f2 at R, and we substitute here, and we find the derivative of x and the derivative of y. Using the parametric representation, we represent C, curve C, by R, and the parametric representation of a circle is A cosine t, A sine t, where A is the radius of the circle. And the radius of this circle is given, it is 1. So we're going to substitute here 1. We will have this vector. The value of t is from, as you can see, the circle, we start from t0, then we finish to t equal 2 pi. So t is from 0 to 2 pi. Then we need to find f1 at R by substituting the value of x is cosine and the value of y is sine. That means this is x and this is y. We get the following. f1, which is y squared, that means sine squared, minus 7y. This is f1, y squared minus 7y, and the y is sine, so minus 7 sine t. Same idea, we find f2 at R. That means we substitute R in f2. What is f2? 2xy, so 2 times x is cosine, times y is sine, plus 2x, 2 times x cosine. Then we find derivative of x is cosine. Derivative of cosine minus sine, t dt. And same idea, we find derivative of y is sine, derivative of sine is cosine t dt. Then we substitute all these in this integral. So the line integral will equal to an integration. T is from 0 to 2 pi. F1, we find it here. F1 is sine square minus 7 sine. Times derivative of x is minus sine dt, plus F2 is 2 cosine t sine t plus 2 cosine t, multiplied by derivative of y, which is cosine t dt. We just simplify the integration by multiplying here minus sine with both. We get minus sine cube plus 7 sine square. Also we multiply cosine with both terms. We get 2 cosine square sine plus 2 cosine square. Then we can use calculator to find this integration or integrate just each term alone. Answer will be 9 pi. Okay, so now we're going to solve the same example again, but we want to convert from line integral to double integrals this time. So by using Green theorem, a line integral will equal to double integration over a region R, partial of f2 over x minus partial f1 with respect to y dx dy. This double integration will equal to, we have to find the partial derivative of f2 with respect to x, and f2 is given. So the derivative of this with respect to x will give us 2y plus 2. This is partial f2 with respect to x minus, now we find the partial derivative of f1 with respect to y. That means derivative of f1, this is f1 with respect to y. Answer will be derivative with respect to y, it is 2y minus 7 dx dy. Simplify this, we will have double integration of 9 dx dy. Put 9 outside, we have double integration over a region R dx dy. And our region R, as we discussed, it is a circle. That means this is the rule of the area of a circle as we study in the application. So this one is 9 and this will be the area of a circle, and as we know, area of a circle is equal to pi r square, and don't forget the 9 pi. R square is the radius, and the radius of our circle is 1 because the equation x square plus y square equal 1. So the answer is 9 pi, which is the same answer that we get it when we convert from double to line integral. The answer was also 9 pi. We have the following exercise from the textbook. Use Green's theorem to evaluate the following line integrals where the region R is bounded by the curve C. So that means you have to convert from line integral to double integral. You have to evaluate this, or you can evaluate using line integral. Homework for you is number 1 and 3. For example, in this one, you need to find the parametric representation of C, and C is a circle. Then you're going to substitute here the value of y and x, and you have to integrate, and you can find the value.